we can 100% do calculus in a way that makes way more sense,
That's what I'm
in
asking.
my opinion, than
Okay,
what we're currently doing.
and that if that's true, then this is my question for you. If that's true, and I know it's true, but if that's true, could that be represented on the chip? Does that revision in how we do calculus, can it make it all the way down to the to computer engineering so we can build different types of chips?
Yeah, I think it could.
All right, Mr. Ryan Charles, thanks so much for joining me on Patterson in Pursuit.
Yeah, thank you so much for having me, Steve. Really happy to talk with you.
Yeah, it's last we spoke on the show, I want to say it was 7 or 8 years ago, and it feels like it was a lifetime ago. And you and I, on occasion, have exchanged some information about things completely unrelated to what we talked about then, which is Bitcoin and cryptocurrency. We've talked about like a little bit of math stuff, a little bit of physics stuff, and it's always been fun. You've always had an open mind when we have these discussions, and I thought it would be a really cool opportunity just to kind of spitball with you and pick your brain and learn how you're thinking about the world and how you're thinking about reality, how you're thinking about maybe like the theory of computation, your theory of mathematics, maybe a little bit of theory of physics. How's that sound?
Sounds awesome, man. Sounds right up my alley. Love to talk about this stuff.
Right on. So maybe we'll just start and you can give a little bit of your background because I know I know only the basics of your story that I know you went to school for physics and then you got wrapped up in cryptocurrency and went a different direction. So maybe you can just explain, give us the story of your background here.
Yeah, let me go slightly further back just because it's relevant to what I'm doing now. I learned how to program when I was 10 years old because I got a graphing calculator called the TI-80 and I wanted to make video games on it. So
Nice.
I learned how to program at a young age, and that would come back to be a theme of my life. Fast forward to university years, and I got really excited about physics and wanted to just understand the universe. And so when I kind of realized that physics would be a good way to try to figure out what's going on in the universe, I got really motivated and doubled down and studied physics. And I ended up graduating with a double major in physics and mathematics from the University of Missouri, Columbia, Mizzou. And then I went to WashU to get a PhD in physics. That's in St. Louis, Missouri, and spent another 6 years studying physics there. So I was between undergrad and graduate school. I was actually there for 11 years. Now I
Nice.
ended up actually dropping out of my graduate school program because, well, two reasons. One was that I got very excited about Bitcoin and found it difficult to concentrate about physics. I'm like, I'm just going to have to go do Bitcoin.
Hmm.
The other reason was I became less interested in pursuing a career in academia,
Hmm.
which is actually kind of an interesting theme today because I feel like more people are realizing academia it has some problems that seem to be
Yeah.
getting worse.
Yeah.
So I think I was right to leave academia. And no, the Bitcoin thing, you and I, we both know all about this. I mean, I was involved in Bitcoin for a long time. Um, I have decided recently not to continue working on cryptocurrency, although this is also a long story. I do have my own blockchain now. I'm not shutting that down in case my users are terrified that I'm going to shut it down or something. I'm just not going to work on it full time, and I don't want to raise money to work on that blockchain. And so that's its own story. But in any case, now I'm working on AI. So when I think about my, what I'm interested in, um, I keep being drawn to highly technical areas like math and physics and
Yeah.
programming.
Yeah.
Programming, actually, more than anything, is kind of the theme of my life because I'm still programming. That's the one thing that was the constant through Bitcoin and
Hmm.
physics and even my childhood. So that's
Okay.
me in a nutshell.
That's very relevant because those interests overlap very heavily with um, my interests from a philosophical perspective. So I'm interested in like the theory of programming. Some programming is fun and recreational. I'm a complete novice, but I'm interested in how these systems work. Like computers are kind of magical. How do computers operate? How can we just type things into a keyboard and then suddenly like things move in the world and we're like typing words or sometimes we're typing
Yeah.
numbers. It's kind of amazing. And then speaking of academia, so One set of problems in academia could be called institutional. Like there's perverse incentives. There's government is heavily involved with grant writing and the peer review system's all messed up. All that is fair game. There's another angle which was totally inappropriate for me to take when I started thinking this way, but I did anyway, and I'm glad that I did, which is trying to analyze the quality of our academic system by looking at the ideas that are being produced by academics across many different domains. Now, it's common to criticize academia via the social sciences, and you say, "Oh, that those there's gender studies is silly," and like that's the low hanging fruit. But the deeper I dove into even the hard sciences, biology and even physics, and then to my shock and horror and nausea, mathematics, I thought, oh my gosh, there's actually theoretical failures here that I had no idea existed. I didn't even know that in mathematics of all domains, you could have radically different perspectives on what's going on in mathematics. So your background in computation is particularly interesting. And I guess that's why I've liked our conversations, brief as they have been. I really enjoyed them with regards to physics because I've noticed a consistent pattern here. I don't know if you've seen this. I don't know how well you're or how much you're tracking the different schools of thought in modern physics and the emerging schools. But there is a group of individuals who have interest in physics and I think without exception have a background in computation that are saying we need new paradigms. The old paradigms
Oh
don't
yeah,
actually work. And I'm thinking about people like Stephen Wolfram, who is hyper computational, the inventor of, Wolfram. He's yeah. You could sing the praises of Wolfram. Also, Yosha Bach is another person. I don't know if you followed his work. He's got an interest in physics. He's hyper computationally focused. And I think what's going on here, and tell me what you think about this. A lot of the calls, let's say, for new physics have some connection with infinity because infinity is not something that can be handled um, according to the high theory of mathematics in a computer. Like computers can't do actually infinitary processes. So if our sophisticated modeling of physics, for example, is being done on computers, how is that working? There has to be some theory that is not in accordance with the high theory of mathematics in order to do computation because
totally.
computers can't handle infinity. So do you have the similar intuitions here? Like, do you also see that problem in physics and then also how it intersects directly with computation?
Yeah, I think the way that you express it, try to interpret what you're saying here from my own lens here, because I agree with what you're saying. You started with something like, there's two different ways of looking at the problems in academia, that there's like a sort of a social science view, but then there's also the ideas themselves.
Yeah.
I think that's a great way of putting it. Yeah, I think we got problems in both of those perspectives, let's say.
Yeah.
So yeah, well, let's address the ideas themselves because it's like what you're trying to get to here. Yeah, when it comes to infinity, so if you study, one of the things I did when I was an undergrad, I decided I got really motivated about physics and I'm going to study physics. Well, I actually spent a lot of time reading Wikipedia because that happened to be in the late 2000s, right when Wikipedia got big enough that it was actually possible to read Wikipedia and learn something. Because before
Yeah.
that, it either was too small or it didn't exist.
Uh-huh.
But there came a sort of a critical mass when there was enough stuff on Wikipedia that you could read Wikipedia and learn things. So there's a time when I spent a lot of time on Wikipedia reading about mathematics. And when you try to get a big breadth of view about mathematics, you come to infinity as a unique concept, let's say.
Yeah.
And you'll come to people like Cantor with
Yeah.
things like set theory,
Yeah.
the things like the axiom of choice
Yep.
and uncountable numbers and the
Yep.
continuity of the real numbers and this sort of
Yep.
thing.
Bingo.
So yeah, so all this stuff. Now, and then you'll be like, huh, that's interesting. Now, bear in mind, I'm a physicist and a programmer at this time.
Okay.
As a programmer, you don't really do anything that's infinite. So we, in the world of programming, like if you look at what AI is doing right now, all AI computations, there's two sides to what they're doing. They'll very often draw up continuous mathematics,
Hmm.
but then what they put in the computer is not continuous.
That's right.
Because of course it's not continuous.
Right.
You can't put that in a computer. What they're doing is in a computer, the way we do it is we deal with floating point numbers,
Mhm.
which is a particular type of number that is basically unique to computers. It's completely unrelated to the sort of, I shouldn't say unrelated. It's not the sort of numbers you study in mathematics. It's a different type of number
Yeah.
that has different properties. Like, for instance, if you add zero point 0.1 plus zero point 0.2, it doesn't come out equaling exactly zero point 0.3. It comes out rounding to something slightly off. And so you can find anomalies like this with floating point numbers because they're a finite representation
Yeah. Yeah.
of real numbers, but they're not real numbers.
Okay,
Yeah,
let
go
me
ahead.
pause you just to explain to the audience because this is like exactly the conversation I want to have. Especially with somebody with the technical heft that you have here, because I'm just like a guy reading things. I can't claim the technical expertise to have you confirm this is wonderful. Okay, so
Yeah.
for the audience, um, in the theory of high mathematics as we have inherited it from really the last century of formal mathematical work, there are different categories of numbers. There are different, if you think of there being different kinds of numbers, let me give you an example. You have the integers, 1, 2, 3, 4, 5, and so on. Then you have the rational numbers. You can think of an example would be 3/4. That's not an integer. Okay. You also have this utterly foundational concept in the high theory of mathematics, which is real numbers. Now, what the definition of a real number is actually quite squirrely, but you can think of it intuitively as saying, imagine that the real numbers are could be talked about as being those which are captured with infinite decimal expansion. So instead of, 0.987, it's 0.987666132 dot 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 and so on. So the idea is that there is an infinity of real numbers, and for example, between 0 and 1, there's supposed to be an infinite number of real numbers. So you can think of, in addition to there being zero point 0.1 and zero point 0.2 and zero point 0.3 and 0.11 and zero point 0.22 and 0.23, you have 0.111 dot dot dot, 0.222 dot dot dot, 0.33 dot dot dot. There's supposed to be an infinite number of them just between the interval of 0 and 1. Okay, this idea is called a continuum. The idea that there's an infinity, there's whatever that means between two integers. We're going to call that the continuum. This is a rough way of describing what's going on here. Okay, here's the problem. When you're dealing with real world computation or computers, how are you supposed to handle 0.1111111 ad infinitum? That doesn't even, the concept maybe doesn't even make sense. Like you have to, do you terminate the decimals? Do you say, okay, we can't handle infinite decimal expansion, so we're going to say we're going to have 900 decimals, and then after that we have to do something else? And so the what you're talking about, floating point numbers, is the attempt that we have to try to take the concept of real numbers and bring them into the real world of computation. And it turns out there's all kinds of to say, you could say, imprecisions or approximations, rules of thumb, procedures, like conventions about how you handle real numbers in the world of floating point numbers. So
Yes.
this turns out to be not just an abstract theoretical problem, an extremely concrete problem that has immediate implications even in things like cryptography. Because when you're dealing in cryptography, you have to be ultra precise in order for cryptography to work. And when you're talking ultra precision or perfect precision, this technique of approximating based on a judgment or based on a protocol to handle real numbers, that can be the difference between secure and insecure. There have been examples of bugs in the world of cryptography that specifically come from this exact problem of floating point numbers. Okay, is that a fair? Do you think I've done a fair job explaining the situation here?
Yeah, totally. I think, yeah, absolutely. Yeah, yeah, for sure.
Okay, so then we're going to get controversial. All right,
Okay.
isn't it interesting to note that like the theory of real numbers, the high theory, let's say from academia, can't work ultimately in terms of the computations we're doing, not just on a machine, but also humans can't handle actualized infinities. We can't do math that includes actual infinities. So what a bizarre situation that there is this almost principled gap between the theory of math and the real high mathematics is all continuous, and then the actual math that we do, which is all discrete, necessarily discrete. So one possible thing going on here is, well, maybe the high theory is wrong. Actually, we need a new theory of math which builds up from discrete foundations. That if people are totally unfamiliar with anything I've just said, you're going to go, well, that's obvious. Obvious, yes, of course. You should build up math from discrete foundations. It would all be computable. That makes a lot of sense. The trouble is that idea turns out to be ultra heresy. That's like if you suggest,
Yeah,
yeah,
totally.
yeah,
It shouldn't be because I 100% agree with what you're saying. Like, I would just to put it differently because I've heard you say things like this before and I've thought about it myself. I think we absolutely need to reground math in a modern way that is somehow finite and informed by the reality of what can actually be computed on a computer, but it can be done at, it's uh, well, I'll just leave it at that. The fact that there's this, I forget the word you use, but some impenetrable wall between the reality of what we're doing when we actually compute stuff, which is all finite,
yes,
and then this mysterious infinite stuff that goes on in mathematics. Um, this makes no sense. I mean, what are they doing? Like what? Like we need a different type of mathematics that's grounded in reality somehow, that is informed by you know the actual things that we can compute and is free from these bizarre paradoxes that you get in mathematics, which we haven't even discussed yet, but they're
yeah,
extremely odd paradoxes. It's like,
yeah,
well, just get rid of all that stuff. There's
yeah.
something wrong with all that.
Now you said something that I wanted to ask about. You said the AI companies, I think you said something like they're writing the continuous theories, but when they try to implement them, they're not continuous. So what's going on
Because
there?
everybody's because what's that? Because everybody's learning math from mathematicians and they're teaching you the real numbers and they're continuous and all this sort of thing. But then they're going and actually trying to do it on the computer and like this makes no sense. We can't do any of that.
Yeah.
But they still use the same equations and they assume the same. They don't want to make the mathematicians angry or
Uh-huh.
uncomfortable. And they're like, well, look, they're a professional mathematician. They've spent their entire lives doing this. They obviously know what they're talking about. I'm just an idiot programmer. I'm a computer scientist. I don't know anything about math. And so they must know what they're talking about. But then when they get down, to actually calculating things, like you basically throw that out. You have a different theory, which is not, I shouldn't say throw it out. I mean, it's not like it's 100%
Right,
incompatible.
right, right,
It's
right.
just it just is what actually works when you need to compute something. And it's, of course, it's free from the paradoxes of infinity and things like this because it's completely irrelevant for the finite, discrete computations that are occurring on a computer.
Okay, so I want to bring this into physics in just a moment, but before I do, I have been wanting to ask this question to somebody and I don't have I like a lot of times I'll be asking questions and they're leading questions. I sort of know the answer. This I truly do not know the answer, and I don't know if you do, so no pressure here. But I don't even okay, how deep does floating let's say the programming structure of floating point numbers get into, let's say, the theory of computation? The reason I ask is if it were possible to come up with a new theory of math and numbers, which is fundamentally discrete and like fundamentally logical, and you don't have to do the gymnastics of trying to make floating point numbers work, is that something that would change how computers operate? Like, for example, when you're thinking about a CPU, how a CPU, or if you're thinking about like a register of how the actual bits are flipping in some piece of code, is does floating point number theory make it at that level of computation? Like, if we were to have the renegade theory, would be how much would we be able to rebuild from the ground up with a different theory of math,
Yeah, okay, so let me
if
fill
anything?
in one piece of detail here because I don't want to get trapped in the world of floating point numbers. Floating
Yeah,
point numbers are not the only way to represent numbers
yeah,
on a computer.
right,
So I'll give you three. There's I mean, you could represent it however you want. In some
right.
sense, it's completely open-ended, but let me give you three common ways to represent numbers on a computer. There are integers, which are just 0, 1, 2, 3, 4, and so on, but in binary of a fixed size. So very common computers, you have something like an int 32, which is a 32-bit sized integer. So it can be all the way up to 2 to the power of 32 is the
Mm-hmm,
maximum sized 32-bit integer.
mm-hmm.
Integers have discrete circuitry in your CPU just for computing
Okay. Can you
integers. So
can you
there's
say that when you say discrete circuitry, are you
yeah,
saying that on the chip itself there are
physically
there are
on the chip.
electrical? Okay, yep.
Yes, there are literally circuits specifically designed for adding, multiplying integers.
Okay.
There are also completely separate circuits specifically designed for adding and multiplying floating point numbers.
Is that so?
Yes, in fact there's actually a whole bunch of them because there's different circuits for adding and multiplying 32-bit integers and 64-bit integers or 8-bit integers or 16-bit integers because
Got it.
when you're dealing with
Yep.
computers you have to deal with numbers of different sizes. So there's actually different hardware. So your CPU has like the notion of adding a number. It's got the same sort of logic like probably I can't even tell you how many times because it would be modern CPUs now also include GPUs. And so they actually have a huge number of circuits that are doing exactly the same thing and capable of adding and multiplying different kinds of numbers all simultaneously. So that's its own, there's a whole world. I mean,
Okay.
I'm not an expert at this.
What
There's
would you
like
call
a,
that? What is that domain called? The mapping of the number construction to the actual hardware. What is that called?
so the field of study, if you study this at university, is computer engineering.
Okay.
That's what it's called,
Okay.
which is different than computer science. They're
Okay.
two totally different things. Computer science is basically software. Computer engineering is basically hardware.
Got it.
Within computer engineering, I actually took a course on exactly this when I was in graduate school. So I actually laid out a microprocessor myself. There's software that you use. There's this tool called Cadence. You can, by hand, draw transistors on your screen. And if you have the patience to draw a billion of them, you could design a modern microprocessor, right? Because I don't even know how many billions of, they used to be hundreds of millions, but I think they're well into the billions now. Like these modern
Okay.
NVIDIA GPUs they're probably tens of billions of transistors. I don't even know. But obviously, no one sits there by hand drawing this one
Right.
transistor at a time to 100 billion of them. But they have, people, but you will sometimes go all the way down and have to deal with an individual transistor. But then your software lets you manage a huge, the whole thing all in one go. So anyway, that's a whole world. That's computer engineering.
Okay.
And if I were to say, you and I have connected about this before, and if I were to ground all of this in theory, um, I would say something more like, you can know all about that. I think that's very helpful, but have a computer engineer sit with you when you reground all of mathematics because
Okay.
they have a practical connection to what this is actually like to compute things that can help ground it. But I wouldn't say that computer engineering itself is the foundation. I would say the foundation is more like just finite numbers.
Yes.
Just we need to somehow come up with notions in calculus and even prior to calculus, notions like, well, if we're going to somehow deal with, you know, computing things in numbers, how are we going to deal with geometry, which deals with notions such as pi and the square root of 2,
Hmm.
which are irrational numbers? And how do we make sense of that if we're somehow going to reground mathematics. Let me finish, but I
Hmm.
just want to finish one thing, and I'll,
Hmm.
I'll send it back to you.
Hmm.
To conclude with the different ways you can represent numbers in a computer, there are integers, there are floating point numbers, which can be, they're also finite. They're the same size. You can have like a 16-bit floating point number. The difference is there's different parts of the number, and so it's written in scientific notation where you have like 6 times 10 to the 3 or something like this. And so there's actually three different parts. There's like I forget what they're called, but there's three different parts. So they're in those bits. There's like the first few bits are one part, then the second. And so the circuitry in the microprocessor is specifically designed to add and multiply those things, but they are absolutely finite. If you're dealing with 64-bit floating point numbers, or actually what most AI systems deal with are either 32-bit or even smaller 16-bit. Suppose we're dealing with a 32-bit floating point number. Well, that the maximum number of different numbers is 2 to the 32. 2 to the 32, whatever that is a pretty big number, but it's not infinite. I mean, it's just
Yeah,
2 to the
right.
32. It's so now that's the second way. The third way, though, is there are other ways that you can represent numbers in computers that can be as complex as you want to be, because you can build on these primitives
Yeah.
to then represent numbers in all sorts of complex ways. So, for instance, in computer algebra systems like Mathematica, or these days people like to use Jupyter and things like this, Mathematica was the first one that I know of. It'll let you represent a number like pi as an abstract concept because
Hmm.
it has the concept of pi built in. And so it can represent numbers like 2 pi, for example. What is 2 pi? Well, it's 2 times pi. Well, what's that? It's like, okay, well, what do you mean, what's that? Do you want to see the decimal representation of that?
Uh-huh.
If you want to see that, then it has an algorithm for generating the decimal representation.
Yep, yep,
How
yep.
many decimals do you want to see? Well, it has an algorithm for generating it up to n decimals,
Yep, yep,
however
yep.
many decimals you want that. So it has the concept built in. So you can do all sorts of fancy things. So in the world of computer algebra systems, they do have a notion of uh, real numbers like pi that is slightly improved from an accuracy standpoint over floating point numbers, because it's in some sense it's you're not you're not you're not destined, or you're not hooked into a fixed number of decimal points or something like that, but it's still finite.
Right.
You're not escaping the world of finite systems here.
So
You're not ever encountering. Yeah, go ahead.
could I frame that as saying the computer is treating pi as a function, and when you can call the function and you specify how many decimals you need, and it will generate how many decimals
I
you
think
need.
that's fair to say. Yeah,
Okay.
I think that's fair to say. Yeah.
Okay. So let me ask you then. Maybe this is a basic question. Maybe not. Why isn't okay? It is there below the floating point structure and the integer structure, is there a baser, or mustn't there be some baser logical structure that's that's common to them both? So let me ask let me ask it this way. Why not have everything integer based?
Yeah, I mean, well, let me answer the question and say, if you want to get to the unifying concept in computers, and computers is kind of its own world, because we're dealing with technology that we have today. And we love our technology. It's amazing compared to the past. But I also think in the future we'll probably have something wildly different. Who knows? But if we're talking today's technology, we're still talking transistors. And so the fundamental unit, let me give an overview of the transistor really quickly. Because the transistor is just an electrical switch that can be on or off. That's all it is. On means one, off means zero, or it could mean the other way around. It doesn't really matter which one's off or which one's one, which one's zero. It can mean whatever you want. But all it is an electrical switch. And so you can hook transistors together, and you can have one transistor turn on or off another transistor.
Right.
So if they're touching, you basically have the first transistor say, if this one's on, then this one's on. Well, then you can start connecting them together in really complex ways. And you can do fundamentally two things with transistors if you start hooking them together. You can do logic, because you can do things like, well, if they're both on,
Hmm.
then I want
Hmm.
the result to be on. If they're both off, I want the result to be off. Or if just one of them is on, then I want the result to be on. That would be an OR gate. You can do OR gates, AND gates, NAND gates, XOR gates. So you can do logic gates this way. You can also do memory. So you can set it and let it just be set, and it'll just stay there. And so it remembers that. With logic and memory, and then
Yeah,
you hook up
that's it.
clock cycle, you can do like anything whatsoever.
Yeah.
So you've got a clock going and you've got memory. You start with some initial state. You've got a bunch of ones and zeros that you're starting with, and then you get the clock going. And it flips one transistor somewhere, which causes all the other ones to flip, and then
Yep.
flip again and flip again and flip again. And so your input gets translated into an output somewhere else. And all it is transistors. And the interesting thing, if I'll just conclude, if you want to say something,
Hmm.
one of the things that you'll learn if you study this in detail, and again, this is basically computer engineering, is what I'm telling you. There are books on microprocessors you can read that will cover this. If you wanted to abstract all of this, everything ultimately amounts to a NAND gate. A NAND gate is not AND. It turns out you can build all logic circuits with NAND gates. So there's two ways you could look. You either say everything's transistors or you say everything's NAND gates.
Yeah, I
Or
like
you say
that.
everything's ones and zeros, whatever you want to say, but it
Yeah.
actually is ultimately not that complicated. The underlying concepts are
Yeah.
quite simple.
Okay, okay, two things. One, I wrote this small book. I don't think, oh, I do have a copy. It's called Square One: The Foundations of Knowledge, and I'm trying to figure out the question, can we have certain knowledge about anything? Can we know truth? And the conclusion I come to is yes, a very limited set of abstract truths that are ultimately grounded in logic. Why? Because it's necessarily true. That is to say, the laws of logic are necessarily universal because it's literally incoherent to think otherwise. So something being some way and not being the way that it is at the same time literally doesn't make any sense. So I think at the bottom of everything of reality is logic. And then here's this very I think this is the move I'm making. I don't know if this is accurate or not, but you can think one way of thinking about what reality is a gigantic collection of states. So what am I talking about when I'm talking about reality? Well, I'm talking about the way things are. What does it mean to say the way things are? Well, things are in a state. That's like the most abstract way I can talk about reality. Things are in a state.
Yeah,
Now,
yeah,
you could, if you wanted to, say, well, whatever that state is can be represented by a bit. It could be a one, or a zero, or maybe a two or a three. So maybe you don't have doesn't have to be binary, but there's lots of different bit states. And then what is going on when reality is operating is the flipping of a bunch of bit states. Why?
100%. Yeah.
Because they're, things are related to one another. And so I sort of am thinking of breaking down reality down to its finest grain components, which is essentially like logic gates flipping. So I do think this fits with the theory of computation you're describing here, that like underlying what the computer is doing is mathematical bit flipping. But then I have this question then. When we have these different, let's say, processors or these different constructions that are designed to be a set of logic gates to handle computations with floating point numbers and a set of logic gates that are handling integer arithmetic. I, I don't know if this is the right way to ask it, but is the reason that they are in different classes ultimately something like a practical geometric question? And here's what I mean: that when we're dealing with uh, electrical wires on a wafer, the the you are let's say the efficiency of your computation depends upon the thing that the actual structure that's on the chip, the where the lines are connecting to dots, if you will. So you can imagine like a purpose-built chip that only flips bits a couple of ways, and it's like, there's a line here, a couple of lines here, and it's like ultra efficient. When you're dealing with the gymnastics of floating point numbers, for example, you have to do it's a different geometry on the chip. It's like a different practical geometry on the chip. So I wonder if there's some weird intersection here where like the reason that we're creating different chips is to try to like we're doing something geometric. Does that make sense?
Yeah, I mean, I haven't really thought about it quite the way that you're putting it. I mean, I would say that that makes sense. I'm sure you can map it. My way of understanding that would be, Can you find a geometric interpretation of what we're saying? And you basically put it in the language of geometry. I think the answer is yeah. Um, but I can't give you a long-winded thoughts about that because I haven't thought about that in detail, but it sounds like a plausible idea to me.
So, like another way maybe of putting it would be, if you think about a a road system, you've got a bunch of possible locations in the road system, and how quickly you can get from here to there depends upon the road. And you can imagine there's like in the simple model, well, the simplest path from here to there is just there's a straight line from point A to point B. But if you have some really complex network, you can't just have one line. You got it. Well, I got to go to the store, and then if there's something at the store, then I'll go here, and if it's not at the store, then I'll go there. It's like this complex logic gate situation about how the route you're going to take with your errands, and that's dependent kind of on the sophistication or the amount of hops you have to take. Let's say the complexity of the route you have to take um, is going to determine the geometry of the road. If you're going to say, I'm going to
Yeah.
do,
So
yeah, right?
yeah, I think I see what you're saying. I mean, let me try to interpret this and see if I'm getting what you're saying right. I mean, there's in some sense, so in geometry, you deal with a metric. So let's suppose you want to make the bigger change you want to make something. You're changing the state of the system into something else. It might have to go a longer way in a sense. You have to
Yeah,
make more
yeah,
complex changes, and
yeah,
it's as though it's going a longer distance when you do that.
yeah,
And so, in thinking about it that way, it is like a type of geometry that you're to go a longer distance is to make a
yeah,
bigger change in the state of the system.
yeah.
Yeah, that sounds like a very interesting yeah way of looking at it.
Okay, okay, cool. So I'm glad you see what I'm trying to get at there. So then I guess this would be the answer to the question I posited before. Why do we have different chips? And it would be something like the computations, the complexity of the computations that are required by floating point, the floating point system is way higher than the complexity of the calculations that are being performed by integer arithmetic. And so you need a different set of pathways. You need a different geometry in order to do this efficiently rather than putting everything into the arithmetical
Yes,
system.
okay, so well actually that's an interesting question. Let me fill in a little bit of information about
Okay.
that. Because you actually don't need floating point circuits in your microprocessor.
Right.
Old school microprocessors from like the 80s did not actually have separate circuitry for floating point numbers. They only had integers. But integers are actually enough. You can
Yeah.
actually program using integers floating point logic with integers. You can use the underlying integer data structures and underlying arithmetic and binary operations to actually program in software the exact same logic that
Yeah.
happens with floating point circuitry.
Makes complete
What
sense.
happens is it's just not that fast because then
Right.
you have software doing more operations on these integers. So what they discover in the world of microprocessors and these days GPUs, we need to make sure that the circuits we're building in are the most useful circuits.
Right.
And so they discovered, well, everybody's got to have these floating point numbers. Why don't we just build in the circuitry for the floating point numbers into
Okay.
the computer hardware itself? And so starting somewhere around, I think maybe the early 90s, maybe it was the late 80s, I don't really quite remember. I was a child, obviously. I'm not, yeah, or maybe it's not obvious, but I was pretty young at that time. I was alive, but very young. They started adding in floating point units into the microprocessors, and they would advertise this. Companies like Intel would literally advertise, it's got an FPU, it's got a floating point unit, it's got a
Got it.
mathematical computation unit in it, and it's
Yep, yep,
and
yep.
they would actually put that on the box when you buy a processor because people used to do that and go to the store and actually buy a physical processor. So, so anyway, but so in conclusion, if you're asking what is the actual bare minimum you need to technically be able to do anything, the answer is not very much. The answer is the modern computers have way, 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 way more than you need to technically compute something. But you want to be able to compute it quickly. So what
Yeah.
do you need to compute the thing that you actually want to compute and then to do it quickly?
Yeah.
You may need custom circuitry for that, particularly floating point numbers, which have proven to be very, very useful. And are, we wouldn't want to go without. We keep adding more in because modern computers with these GPUs, we're actually continuing to add in more and more and more and more floating point numbers or floating point calculators because it turns out that those are actually extremely helpful for the sort of calculations we need to do all the time.
Okay, okay. So let me ask a question here that I'm getting a little bit closer to an answer. Um, so my intuition is to say, let's clear out the dead wood and we'll rebuild from new foundations. That's just how I like to think about things. In this case, it sounds like, let's say, the floating point system is a bunch of helpful shortcuts that are sort of clunky and complicated, but they are more efficient than putting everything into integer computation. That makes a ton of sense to me. But here's the question. Um, in theory, Theoryland, could there be a way to do the type of calculations that are being done with floating point numbers, let's say with different steps? So in other words, I'm saying I look at this from the abstract and I say, well, isn't it interesting that the computer engineers are trying to build chips to make floating point numbers work more efficiently when the theory comes from real numbers and the theory of real numbers is wonky? So could there be
I
some?
think
Yeah.
I would just say I think honestly in the world of computer engineering, they're not trying to do real numbers. They're not even trying. They're trying to do
Okay.
floating point numbers, right? The computer engineering
Okay.
people had to invent floating point numbers
Well,
because
that's
the mathematicians
right. Right.
didn't have a solution to their
Well,
problem. Yeah.
that's what I'm saying though. Is the 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 there's still this connection between the practical people are trying to say how do we do with real computation what the mathematicians claim they can do with real numbers. And I'm wondering if it's sort of like I would want to avoid a situation where one is trying to model the ability of real numbers when the theory doesn't work. So if somebody is totally not thinking about real numbers at all, they're just trying to think about real world practical computation. I wonder if there's like a different way to build things up that allow you the precision, that give you the precision of integer based arithmetic, but the efficiency of the floating point uh, numbers. So in other words, like maybe there's a bunch of computations, there's a bunch of hoops that are being jumped through that don't need to be jumped through because that branch of math is unnecessarily complicated because the people that originated it were still operating within a math paradigm that's kind of flawed. Is that a preposterous thing to think?
I mean, if you're saying, I think there's because I see it as two different problems here. If you're saying there's a better way to do uh, computing useful results,
Yeah.
or something like that. I mean, at this rate, it's hard to say because there's so much momentum behind the current approach that there's a lot of value in just continuing to do it the same way,
Yeah.
even though there may be some more optimal way in some hypothetical sense. Like I would say that's the realm of like computer engineering research is like, is there some other type of number that's not an integer or a floating point number, if this is what you're saying, that would be more efficient for practical utility or something like this.
Yeah, it would be integers, but it would be different ways to manipulate the integers to get the output of the floating point numbers without the steps that are undertaken with the floating point numbers. So in other words, like
I
yeah,
think the way you're saying it honestly sounds backwards to me. It's if you
okay.
try to do it with integers, you're going to have more steps. That's why they invented floating
but
point
but
circuits.
it's not the integers per se. So in other words, the integers are the the hubs, and the logic gate is the set of steps to another hub to the other integer. So what I'm saying is maybe the integers are good enough to do compute. In fact, I think probably in a new theory of mathematics, one could make integers the foundation, I think successfully. It would be like the function that you're doing on the integers to get the outputs of calculus wouldn't be the same steps that they are when you take the floating point number approach. Does that make any sense?
I don't know. I mean,
Okay.
I mean, okay. I'm not really sure. I'm not sure I
Okay.
understand what you're saying,
Let me
actually.
ask a completely different way.
Yeah.
Do you think that it could be that one could do calculus in a different way altogether than the way that we have been
Okay.
doing calculus? Yes.
Let me answer this 100%.
Okay.
I have very detailed thoughts on exactly this question.
Okay.
We can 100% do calculus in a way that makes way more sense,
That's what I'm
in
asking.
my opinion, than
Okay,
what we're currently doing.
and that if that's true, then this is my question for you. If that's true, and I know it's true, but if that's true, could that be represented on the chip? Does that revision in how we do calculus, can it make it all the way down to computer engineering so we can build different types of chips?
Yeah, I think it could.
Oh, wow.
Let me explain. I want to explain my idea here because this was something, man. I tried to explain this to people when I was in graduate school, and then they didn't know what the hell I was talking about.
Okay.
And it's one of those things when that's kind of why I left graduate school because I'm going to tell you an original idea I have
Okay.
that I have never been able to get anyone to understand just what the hell I'm talking about. But you're probably the closest to being able to understand what I'm saying on this particular subject that I've ever encountered someone.
Okay.
So there is a different way to do calculus that is very similar to something called non-standard analysis,
Yeah.
which is actually a different approach to calculus than the usual one that you learn at university.
Yes.
Non-standard analysis is actually more related to, I think it was Leibniz was one of the original guys that invented calculus, if I remember the right guy. Some of the original calculus was based on infinitesimal numbers.
Yes.
Um, now, that's fine, and people can study that. My approach is actually slightly different. In a way, mine is the exact opposite of infinitesimal numbers.
Yeah.
Mine is based on finite numbers.
Yeah.
And it's based on the idea that what you really want to do is, if you're doing calculus, you're really doing something like if you study calculus, it comes down to doing things like computing a derivative, which is like essentially the rate of change of a line. And if you go all the way down to like a really small level, it could be like a discrete change in that line, right?
Yeah.
And sometimes they actually teach calculus this way. They're like they
Yeah.
intuitively make you understand.
Yeah.
It's like a small step.
Yes.
And then they're like, but then when the mathematicians formulated it, they
Uh-huh.
threw all that out the window.
Yes, exactly.
But what if a small step was actually just a normal sized step?
Yeah.
And instead, what you realize is a derivative is literally a change that's like a step from one to another.
Yes.
And if you want it to be related to calculus as we understand it today, what you do is you zoom way out.
Yeah.
You just have a whole bunch of really small steps.
Yes.
And those really small steps are the rate of change. And the integral, of course, is the exact opposite, which is just adding up a whole bunch of like lines.
Yes.
Now, it is my opinion, and I've partially worked this out. I don't think I couldn't, there's no document or something I could show you, but I have spent time and effort working on this. I'm absolutely certain this can work, and this makes way more sense. It matches
Yeah.
the way computers actually work, and in my opinion, it matches the way that we actually think about what calculus
Yes.
actually is. And
Okay.
it makes dramatic, and it's free from any of the paradoxes
Yes, it
of
is.
infinite, real numbers.
So we've never talked about this before, but yeah, I agree. Uh, a couple of things on this. So this sounds like this is one of the domains I'm researching, and this sounds like the finite difference method. So when you think about a derivative, here's a problem. When you're talking about a derivative, as it can be spoken about in physics, as a rate of change. Well, a rate of change doesn't make sense if you're talking about it being an instantaneous rate of change. No, a rate of change requires 2 points, and it's the difference between 2 points. So
Yeah.
if you're talking about integrals, for example, does it make sense to talk about the area of a rectangle with actually zero or infinitesimal, whatever that means, width?
Yeah.
No, a rectangle by definition has to have width. Otherwise, it's not a rectangle. So if
Yeah.
that's true, our theories of calculus are wrong because our theories of calculus are trying to say the integral is the area underneath the curve where the the width approaches zero. what does that mean? Is it zero or is it non-zero? And they go, well, it's infinitesimal. Okay, is that actually a number? Can you say what the width is? They go, "Meh, well, it's a kind of a magic thing. So I've been, yeah. So okay, a couple of things. You might be interested
This
in
is
this.
it. I'll let you continue, but I just want to say, I think we're narrowing right in on what I think is actually the heart of the issue in a way.
Yes.
If you can solve this problem and write it up in a clear way that's compelling, I think this whole approach makes so much more sense. And it's completely free from the paradoxes that you encounter in continuous real numbers. It's this it. If you can solve, there's I would say two things: calculus, and then deal with pi. Because
Yep. I
I've
got it.
thought about calculus. Okay, I'm curious
I
to
got
hear
that
your
one.
answer
Yeah.
because the other one is how do you make sense of something like pi
Yep.
if can you tell me
Okay.
because
Yes.
I don't have the answer to that
Circles
one.
don't exist. That's how I
Okay,
like to
yeah.
say it. Okay.
Okay,
Let me be a little more specific. Okay. What is meant by pi? There's two different ways to try to answer the question. One is the traditional answer, which is pi is a geometric phenomenon. Pi is the ratio of a circle's circumference to its diameter. There's another way of trying to answer the question, what is pi, as you think about it as a number. What is the value of pi represented by numbers? So I'm going to say that in the worldview in which space itself, that is to say, the domain of geometry, is fundamentally discrete, it is necessarily logically the case that pi is a rational number. That is to say, if you're talking about a circle, an actual geometrically extended thing, there's a
okay,
number of
yeah.
bits that are the circumference, there's a number of bits that are the diameter.
Yeah, reality has a resolution would maybe be a
Yes.
different way of putting it. Like
Yes.
you run into a limit somewhere where pi doesn't go past that
That's right.
because reality itself doesn't go past
Exactly.
that.
Exactly. So you could think of whatever the ideal circle is in a logical system. It is not the circle that we've been told from the continuous theoreticians who want to say it's something magic. And there's all kinds of magical properties of pi. For example, because it's supposed to be a non-repeating infinitary sequence, that means that all possible information that could be represented with digits is, according to the standard theory, somewhere in the decimal expansion of pi. That includes Shakespeare. Did you know Shakespeare is word for word, in binary for that matter, captured in a circle? Okay. Why? Well, because infinitary decimal expansion plus non-repeating number equals all possible information structures are in pi. Or there's a crazy, a way crazier alternative, Ryan, and that is to say, those circles don't exist. Reality has a base unit. There is a
Yeah,
fundamental resolution, and so there is no problem. There's no problem with pi. It goes away.
yeah. I mean, maybe that's the answer right there. Yeah, I mean, yeah. I would have to. Yeah, I mean, I haven't thought about the answer exactly the way you're putting it there. So, but it has to be something like that because there. Well, I agree with you. I'll put it that way. I am
Okay.
curious to hear more and think more about exactly the subject. Yeah.
Yeah, yeah. Okay. So a couple more things. One is I don't know if have you heard of Norman Wildberger, the mathematician?
No, no,
Okay,
that's a new
so
name to me.
there's a Canadian mathematician who taught in University of New South Wales in Australia for like several decades, and I actually flew to Australia to speak with him several years ago. He's the whole reason I took a trip there because I admired this guy. He is trying to build and has built out fairly impressive mathematical structures that eject real numbers from math altogether. No transcendental functions. He has what he calls rational trigonometry, no sine, cosine, and tangent. He's also dipping his toe into physics and trying to just completely eject completed infinities and real numbers from math. And he's had great success in doing so. He's got like a YouTube channel now. And anyway, I find him very, very exciting, and he's got credentials to back him up. And he's just walking down this road of what math might look like when we go the discrete route and get rid of real numbers and infinities. And I have always wondered, I have not asked him, but I have always wondered if, let's say, his theories of math are workable or usable, I'm gonna expect they're more efficient in many ways. Could his theories somehow be brought down into computers? Like if we were to build a chip based on rational trigonometry and not, which is a different, he approaches things differently. So he gets around the problem of the square root of two. He gets around problems with pi. Is that something that could have practical effects in terms of the structure of how we build chips? That's the question I'm desperately trying to answer. Because if we can rebuild computers with better math, that seems like a holy grail to me.
Yeah, I don't know. I mean, to be honest, I'm less optimistic about that just because, from my point of view, the engineers are the ones that have it right. It's the mathematicians that are wrong. So, if anything, I want to rebuild
Yeah.
mathematics using computer engineering,
Okay. Yeah.
not the
Yeah.
other way around.
So I guess what I need to do, especially after this conversation, is I need to talk to some computer engineers and see whether or not they're trying to play nice with continuous mathematics. Because if they're trying to
I
play
wonder,
nice,
there's, yeah, there,
yeah,
no, there's, I do wonder, like, there's got to be some computer engineers out there that are thinking the same thing we're thinking, right? I
yeah,
wonder, because then whoever they are should be in touch with the mathematician you're talking about. Because
yes,
somebody, I did study mathematics in undergrad, and I mean, it takes an enormous amount of work to do the sort of thing that we're describing.
right,
If math has the sort of flaws we're getting at, where it's in the real numbers, this is so embedded in all of mathematics and all of physics and all of science
yes,
that redoing all the work that's built on these poor foundations is, an enormous amount of intellectual effort to redo all that.
yeah,
So having someone sit there and concentrate and do it and start that is very valuable, so that there's somewhere to begin. And but yeah, there's a lot of work to do to finish it. So you need those people. In my opinion, I do think that computer engineering is relevant because
for
I
sure,
don't see a problem with computer engineering. To me, computer engineering is, well, it's a proven practical thing. They had to do math differently. It's not, I mean, well, I think that's fair to say. They had to do math, had to invent floating point numbers. It's a computer engineering invention, as
right.
well as other types of numbers, to actually be able to do practical calculations. And it's quite different than anything that you study in math. I've never seen a mathematician even talk about floating point numbers. Do they
I,
even know what a floating point number is?
probably not. Okay, so this is so interesting because in I don't know, I have never spoken with a computer engineer, but I have done a lot of research in a lot of domains, and I am always deeply underwhelmed by everybody, and I always see unbelievably dogmatic patterns in every domain. So I don't want to rule out the possibility that early computer engineers. You also got to think the early computer engineering is stretching back to the middle and earlier of the 20th century, where you had great mathematical giants like John von Neumann, for example. Everybody is deferent to. I could tell a story. I have no idea what is true. I could tell a story in which 2 years from now, I'm going, oh yeah, well let me tell you what happened in computer engineering. There were the engineers got bullied into submission by the untouchable, great, brilliant mathematical geniuses of the 20th century, and they made some fundamental designs that were trying to accommodate the theory of real numbers, the theory of continuous mathematics. And from there, that was kind of an original sin. And we've been building off, for practical reasons, we've just been building off those original sins. No idea if it's true, but it
You
might
have
be.
yeah, you have a different perspective though, because you seem to be as though saying these computer engineers are somehow trying to do math. I think they were trying to do something practical, at least from my point of view, and I don't know the full history and all this sort of
Right,
thing,
right.
but I honestly think they're really coming at it from a way more business oriented perspective, where they're
Yeah.
literally just trying to make something that people
Okay.
use, and
But
that's why they couldn't do it. Like that, you
I
can't do real numbers
I love
on a
that
computer.
idea. That might be true, but if that's true, if that story is true, then it tells me, okay, well, maybe there's an opening here for computer engineers to try to do math, but good math.
I 100% think so. I absolutely, I can't believe. Well, I think we're just at a unique moment in history. I think, whether you initiate something like this or you're the mathematician that you know or something like this, there is no way math in its current form is going to last hundreds of years.
Agreed.
It's going to become increasingly incongruent with the world of computing. I don't know how it doesn't become
Yeah.
obvious to everyone that as computers grow and as we continue to have the foundations of computers in our lives, you study computers and you study math and you go, we're using computers for more and more stuff. And the way that they deal with numbers is completely unlike the math that we're taught in school.
Right.
What is this about? How do we there's got to be some different way to ground mathematics that actually makes sense and is congruent and not incongruent with the reality that we see around us.
100% agree. So let me then try to transition this to physics. So I think, ironically, it depends on who you're talking to, but some people who are familiar with the intersection of math and computer science are going to go, okay, yeah, you guys are saying plausible, reasonable things. But when you try to transition it to physics, it sounds even more preposterous. Where you go, hang on a second. You mean to say that these concepts that are so fundamental are also fundamental in physics? And just how fundamental? Like if one is rebuilding math from the ground up, does one end up rebuilding physics from the ground up? How tightly are these two things connected?
Okay, so this is a great subject. This is also something I studied in graduate school and have studied it over time since then. So in modern, like if you look at mainstream modern physics, let me try and say this as delicately as I can, because I will both defend physics and attack physics simultaneously. It's a bit of
Okay.
a subtle idea. I think mainstream textbook physics is actually extremely accurate and useful. It's very proven. The stuff that you learn in undergraduate school or undergraduate physics education, classical mechanics, quantum mechanics, electricity and magnetism, is actually all basically correct. With that being said, there is this underlying issue with mathematics that you and I are getting at, which is absolutely incongruent with the actual reality of building a physics experiment and doing calculations. If you break physics into, say, three categories, sometimes people will break it into two, it's experiment and theory, but you could also break it into experiment, computation, and theory.
Hmm.
I would say experiment and computation are out of whack with the theory. And because a lot of the theory is grounded in stuff that doesn't make sense. Now, again, I want to defend physics before I attack it again, though, because the most physicists are actually incredibly practical and basically look at the part of the physics that actually works, and they basically just forget about the stuff that doesn't work. You just don't talk about or deal with the parts of the equations that are completely nonsensical. And it's like, this makes no sense. You've got some infinity in your calculus. What do you mean it gives an infinite value here? This makes no sense. How are you gonna, how's it going to show up in an experiment? Infinity? And they just ignore it. But it's not as bad as it sounds, because it is true that when you focus on the stuff that works, that it actually does work.
Hmm.
So there's something true about mainstream undergraduate physics, but there's absolutely something totally wrong about the foundations as well. And I think that I think I've heard you say this. I'm just going to jump the gun on it and get right to it, which is that there's something wrong with space time, because space time is based on the real numbers. If you look at Einstein's theory of special relativity and general relativity, it's all based on real numbers. If you look at quantum mechanics, it's based on real numbers. Now, you can ground, I could show you in detail. Again, I've got parts of this written up, but not in the form of a paper or something, but I've worked on exactly this. You can reground quantum theory on finite numbers. I'm absolutely certain most physicists do it. If you look at how quantum mechanics textbooks work, they very often will start with finite quantum mechanics and then do some magic and end up with continuous numbers.
Yeah.
It's in that magic that you get all sorts of problems that everybody just always sweeps under the rug and forgets about and never talks about. So I'm certain that there's a core of physics that's totally correct and totally true and accurate, but it does need to be re-expressed in a sensible way,
Hmm.
grounded on mathematics that's not fraught with contradiction. But I also think there's totally nonsensical physics too that is never validated by experiment. Um, and that's a whole other subject, which is somewhat well known. As people have criticized string theory in recent decades, and physics still hasn't made progress. So to move past that. But in a nutshell, I am of the conviction that space-time, in the sense of four parameters that are real numbers, is absolutely not what's going on. But that idea is mainstream physics. If you read mainstream
Hmm.
physics textbook, they all treat space-time as some real existent thing, that these real numbers, which are infinite upon infinite, that that there is no ground floor to reality, that you can go as small as you want. The thing is, it just flatly contradicts physics itself. We have too many experiments to say, no, 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 you can't go down as far as you're saying. It's not true.
Right.
So it needs to be regrounded, and I think it needs to be regrounded using exactly the mathematics we were just describing.
Yes.
That it's ultimately discrete. You need to use discrete mathematics, and I'm certain, because I could give an overview of how I think it would all fit together and work. I'm certain it would work if people had the patience to sit there and work it all out. It takes time and effort,
Yeah.
but this is where we come back to academia, because this sort of thing has never been funded to my knowledge. The government doesn't fund this. People
Right.
working, you can't work on this at a university because it's too weird and different. And they're like, you'll be ostracized trying to do this at a university. You could never get it done.
Right. So, a few points on this. From my understanding of history, the spirit of early quantum mechanics was discreteness. So, specifically, like quanta means like a discrete packet, and what people were learning in the first part of the 20th century is that the energy emitted by light seems to not be in a continuous stream. It's in like discrete packets, like things will jump around and emit discrete packets of energy. And from my understanding, now it's been a while since I've read this, so somebody maybe can correct me if I'm wrong here, but I believe there is a letter from Einstein, I want to say it was to Schrodinger, where they were touching on the idea of whether or not space itself was discrete. And I'm paraphrasing, but I'm pretty sure Einstein said, uh, if space is discrete, then relativity is kind of a castle in the sky. And it would make a lot of sense for space to be discrete, but we don't have the math for it yet. The math that we're using is continuous, and we don't know how to do this within the parameters of discrete math.
Well, that's a great point. I never thought about it the way you said it like that. But, Einstein was limited by the mathematics of the day, for sure, because he didn't know the mathematics of the day and he had to go out there and ask mathematicians. This is actually part of his story. Like if you read about his life history, um, he literally had an intuition for what general relativity would be and had to go out and literally interview mathematicians and get ask for help from mathematicians who of course taught him this standard paradigm in mathematics. So Einstein was constrained. Einstein was essentially indoctrinated into the mathematics of the day to do everything their way. So yeah, I think that there needs to be a new way, and that way doesn't I don't know if I want to say it doesn't exist, because maybe the mathematician that you know about exists. It's not mainstream. If there's a
Right.
solution to this, it is not a mainstream solution that someone like me has ever seen.
Yeah, I don't
Um,
think Wildberger has hit the holy grail yet. He might have. I haven't looked into it in great detail. I know one branch of it that he seems to have worked out is trigonometry, but I don't think he's gone all the way down to reformulate the whole thing. There's actually a funny tweet somewhere from this guy I mentioned, Yoshibach, who's interested in physics. He's like heavily computational, and he, oh man, I wish could bring it up. He was implying, I don't know the history here, so maybe he's incorrect, but he was implying that early Stephen Wolfram seemed to be walking down the road in his development of his proprietary mathematical system, that he could have gone that road of going all the way down to the foundations. And Bach has this funny quote where he's like, something like, we could have had a new math, but instead we wound up with a very complicated and like patented version of Lisp or something. It was like a quip saying, this nice ambition, but you didn't quite get there. And I wonder if I need to talk to him at some point. He's on my list of people to talk to. I wonder if there are people out there right now that are trying to work on this exact problem that we don't exactly know
I
their
bet
name.
so, because I really think that there's something wrong with universities and government funding that are just funding all the wrong things. I'm certain there are people that have the same flashes of intuition and have started the same conversations you and I are having right now. I'm certain they're out there. But they basically get suppressed and ostracized out of academia. You just can't get funded to do this sort of thing because it's too disruptive. It's like if you tell people you're going to change all of mathematics, it's like that threatens every mathematician, or they feel threatened. They
Yeah.
shouldn't feel that way, but they do. And it threatens the physicists. Again, they shouldn't feel threatened either, but they do feel that way.
They should. Well,
And
I would correct you there. I do think they should feel threatened. I think that's very accurately picking up on something that if it turns out they have been building castles in the sky,
well, that's a good point. That
you
too.
know,
I think, and I think there are a lot. You have two sides. You got people that are honestly pursuing the truth, but you absolutely have the physicists that are willing to just literally they know that there's a problem, but they
yeah,
cover it up
yeah,
because they don't want to because it would hurt their ego if they had to admit they were wrong about something. It's like, oh, so you're going to let all these people believe something that you know that goes on for sure. Yeah,
yeah, and well, and I think it would also threaten their careers in the sense that, and their social status, very importantly, perhaps more importantly than their careers to a lot of these people,
yeah,
if this level of error has been made for such a long period of time. In our culture, we are elevating the mathematicians and the physicists at the highest level of the intellectual pyramid. And if it turns out that the at this level you get deep errors, and we haven't even talked about the paradoxes and the
yeah.
contradictions that pop out from pretending like you can have actualized infinities, it's kind of embarrassing. It does not reflect skillful reasoning if one has made peace with a bunch of contradictions that pop out. The other thing I wanted to say, hang on, give me 1 second. It'll pop back in my head because I was like, oh, this is an important point.
Yeah, yeah, go ahead.
Oh no, it was a beautiful train and it just off in the ditch somewhere. It was a tragic accident. 100 people died. Oh, it's a shame. It was about academia. No, it'll come back. I'll shout
Okay,
it out when it comes back.
okay.
Okay, so it sounds like you and I are looking at the same thing, and it's we have to figure out how to do calculus in a real way that doesn't include real numbers and is logically airtight and perfectly understandable to mind and to machine.
100%. And I'll say that um, I got a couple of things to say about it. One thing is that it's not as hard as it could be. Because again, I would just point to look at the AI world. In the AI world, people are doing massive computations, and these massive computations are extremely useful and very proven. They have derivatives. I mean, the basic idea of modern AI theory, if you look at the way machine learning work in neural networks, there's a concept called the something called gradient descent.
Hmm.
I don't want to explain the whole thing right now, but there's a derivative is a very central idea in modern AI. It's like in a sense, it's the central idea,
Yeah.
something called gradient descent.
Hmm.
It's a finite derivative.
Yeah.
Like they're doing calculus, they're doing it in a very practical way. It's a finite derivative. That's what they're doing.
Yeah.
The form of calculus they're doing is finite. So I think there's a lesson. Like they're already doing it the right way because
Yeah.
it's impossible to do some sort of continuous thing that the mathematicians are talking about. They don't even pretend or try.
Yeah.
They
Yeah.
still will write papers using the continuous form of derivatives and things like this. But what they're actually doing is a completely different thing, which are
Okay.
finite derivatives.
Let me ask you on this specific point. So you say they write the papers, they're continuous mathematics, but they're being implemented in a finite way because they have to be. Okay. Is what they're doing effectively truncating supposedly infinitary processes? Or are they actually doing like different steps in the computation? So does the computer's version of calculus look completely different than the human version of calculus, except just truncated, right?
Yeah, okay, so this is a complex situation because to some extent they are truncating, and there's a whole lot of approximations that go on because they're very practical, and so they're trying to get things done. So there is absolutely a lot of truncation that goes on, but that might be different than your question is. But is truncation some sort of logically necessary thing? Like, does that mean it's in principle always imprecise, or does that just mean that they're they're cutting their computation in half by truncating stuff, and getting things done faster. I think it's mostly the latter. They're mostly just trying to get their computations done faster. They intentionally truncate things. So with respect to whether is it in principle truncated? Are they always going to be imprecise? I think the answer is no. You can be absolutely correct using finite methods. And I'll give you a
Yeah.
very simple answer why. The answer is, well, what information are you actually plugging into the computer? It's finite. So you don't to perform your calculation, you're starting with something finite. You're not starting with all infinite digits of pi. Never are you doing that. You're plugging a finite problem
Yeah.
into the computer and you're getting a finite answer. Nothing about that has to be truncated.
Right.
You know,
So I
you
want
can
to
get a completely accurate answer. Yeah.
let me try to put that in a different language, maybe more general. A mathematical system necessarily has a base unit. That's going to be the claim. Now, the size of the base unit relative to the whole system might be flexible. So you can use 32-bit computations, you can use 64-bit. But at the end of the day, at any given time, there is going to be a base unit. That's the claim I'm going to say is happening in math. It's happening in physics. And I think the reason for that is because it's happening in our minds. The way that we think about math is that there's always a presupposition of a base unit that is, in general, fine enough grain that the constructions you see appear continuous. Just like when you're watching a film and it's 30 frames per second, you're not your experience is that you're seeing a continuous visual thing happen, but you're not. You're seeing 30 frames per second. Every
So I
single, yeah, go ahead.
100% agree with you. I want to reinforce exactly what you're saying because I want to say there's a question about whether there's a real underlying physical unit or whether we always assume there's an underlying physical unit. Let's take these two questions separately. I think that approach is totally correct. Either way, we must assume there's a base unit. Whether there's really one is a separate. But in the way that I started reformulating calculus myself, I took that approach because I think it's the only practical approach. So I would almost agree, almost literally word for word, and even the way that you emphasize it with what you just said there. There's like always a base unit. And in my opinion, this is how you can redo calculus.
I agree.
So you start with the base, and the base unit is not an infinitesimal. It's just the base unit.
It's
It's a
one.
normal number. It's just one. Exactly.
It's
It's just literally the
literally
number one.
one.
It's literally
Yeah.
so let me 100% agree with you and build on that slightly. Yes, it's literally the number one. Literally, that's what it is. A meter is a whole bunch of ones put together.
Yes.
And the number 1 meter, a meter is literally a physical distance. Okay. Of course. I mean, a meter is whatever size a meter is. It is a number of units, and that number can be determined. You know what it is. It's if a 1 meter, so if the speed of light is 2.99 times 10 to the 8 meters per second. And you can define this in a way where 1 meter is, I think I'm trying to do it in my head and I haven't done it well. I think it's 2.99 times 10 to the 10 to the 8. Now I'm confusing myself. 2.99 times 10 to the I haven't done it long enough. I'm embarrassing myself as I try to remember what the hell the speed of light is after all this time. 2.9, whatever the hell it is. It's a
Hmm.
number
Yeah.
that it is literally a number of units and it's literally just a number.
Yeah.
End of story.
Yeah.
So when you start doing math, I want to approach, we talked for a while. I'm happy to keep going. You can end it or keep going if you want to, but um, there's a related problem that you encounter when you discuss exactly this issue, which is the notion of dimensions and units.
Yeah.
So this is one of those things where when I studied math, I was so obsessed with understand. I want to understand what you're talking about. And so I spent enormous time, so much time learning. I would read textbooks and doing math problems and things, trying to understand and reading Wikipedia and these sort of things. And one of the problems that no one ever answered, I could find no answer to this anywhere ever. What the hell is a meter? No one would ever give a mathematical definition of a meter. They would just throw it in there and start using meter. So you would have an equation that was all numbers, and then they would just add in the letter M for
Hmm.
meter. and just start using M in there. And they were throwing other letters like S for second and kg
Hmm.
for kilogram and things like
Hmm.
this. Like, what the hell is this? What are you doing? Like, this doesn't, what does that mean mathematically when you just put the letter M in there? And my firm conviction, having thought about this, is that M is literally a big number. It's
Yes.
just 2.99 times 10 to the 8 or whatever it is. That's it. End of story. And
Yeah.
you could look it up on Wikipedia. It's a long number.
Yes.
It's literally that number is a meter, and a second is either one. And again, I'm confusing myself. I'd have to give my. We'll do another talk some other time, and I'll have
Yeah.
the
Yeah.
correct answer. I think it's just one or something is the answer for a second, but or it's the other way around. Maybe a meter is one and a second is 2.99 times 10. That might be what it is. In any case, no, it's not. A meter has to be. Anyway, I don't want
The
to. I don't want
details
to
don't
spit
matter. Yeah.
the data, but it's literally a big number. It's a
Yes.
finite number. It's not an infinite number. It's not a mysterious number. It's an integer. It's just
Yes.
an integer.
That's okay. So yes, now exact same concept applied to circles, and that's what pi is.
Okay.
Or it's a ratio in that case of two
Yeah.
integers.
Yeah.
Because what circles are extended, if you're talking about an
Yeah.
extended geometric object,
Okay. So this is a really ooh. Okay. Yeah. Yeah, so it would definitely be finite. I mean, certainly if you were to draw so if a meter is a number, that's the resolution of reality. It goes all the way down to one, whatever that is.
yeah,
You put those in a circle, that's
yeah,
it. That's 2 pi.
yep,
That number goes down to a certain limit somewhere. It's not an
correct,
infinite decimal. Yeah.
correct. It turns into a square, right? So at that point, if you're talking about four
If it's
units,
very small,
exactly.
yeah,
And
you go,
and
yeah.
so what you can say is the larger the circle, the pi actually
Ooh,
changes. And
ooh.
there's a rate of curvature which actually changes too, because here's an interesting question. How do circles actually get generated on computer screens with square pixels? Well,
Ooh.
the edge of the circle actually changes depending on its size. It gets smoother as it gets bigger.
Okay, I think that's a great way of. I'd have to go back to the foundations of geometry and remember how this is actually defined. But if 2 pi is the circumference of a circle, well, it depends on how big the circle is, doesn't it?
Correct. Yes.
Because if it's a small circle, it's so discretized that the pi is actually different.
Yes.
And so that's a great way because then I think, well, how would you define pi? Well, then pi would be defined something like you literally have to pick the size of the circle you're talking
Correct.
about.
Correct.
And it's defined with respect to that size circle.
Correct.
And
Exactly.
so it would get more precise, as you get bigger. But
Exactly.
but there's no how
But
big do you
but
go?
but
Like you have
also
to give a limit.
it's sort of like a question of megapixels. You go, okay, well, the larger your resolution, the smoother the image. It becomes obvious when you think about that. If that's actually what circles are, then the more you zoom out, or the bigger the circle is, the smoother it is going to appear. Literally, just exactly like how displays on a screen work.
Yeah.
Like if I actually, it's funny. I have
So
this.
pi is not really a number, is kind of what we're, and that's probably why you said earlier. So maybe pi is a function. Maybe that's the way to
Yes,
think about it. Maybe
I
pi
think
is a function. It's not a number.
yes, and I think that's also the way that computers. Let's say, I think that's the way that computer graphics are going to understand pi.
Yeah, I think this is a great way to think about it. I think that's really good. That's a really good way. That explains. That's a great way of roping that into computers too. Literally, that's what they are. So when you have, by the way, there is a branch of mathematics or computer science called algorithmic complexity theory, I think if I remember correctly, that studies stuff like this. So I actually used to own a book. I got rid of all my books. It's a long story, but there are what we're talking about is something like a function, and you can define this in math or in computer science because computer scientists sort of have their own way of looking at things, and it's a function. So that would be a great way to define what are we doing when we're dealing with a number like pi.
Yeah.
Well, if we have an algorithm for computing the digits of pi, then what it literally is a function. Forget about saying, oh, it's a
Yeah.
number. It's not a
Yeah.
number. No, it's not. A number is 0, 1, 2, 3, maybe not even zero, but 1, 2, 3, 4, 5, or
Yeah. Yeah.
whatever.
Yeah.
That's a number. Pi is not a number. Pi is a function for computing numbers. It can give you 3.14159. It's a
Yes.
function for computing numbers, is what it is.
Yes, I think that's correct, and I think that also, if you think of the circle being structured like that, then there is in the strictest sense, there is no pi per se as one number, only because the the magical pi, the transcendental pi, is a way of talking about the property of an object that I'm going to say is actually logically incoherent. I don't think the Platonic infinitely smooth circle makes sense at the logical level. And so this is a funny way of thinking about it. Pi, the transcendental pi, only describes that circle. Pi doesn't actually describe, because it's any other circle that we encounter, any circle that we think about, that we represent. Nowhere are we going to actually be encountering the Platonic perfectly smooth circle. And so the magical pi, the transcendental pi, literally doesn't apply to anything. It doesn't anyway, because we always have to
Yeah.
truncate it.
Yeah.
So suddenly all of that incredible magic and mystery and the stories that are told about pi, my goodness, it all evaporates, and you're like, oh, you don't need this at all. You literally don't need it at all. You can have if you want it to be a uh, a decimal expansion. You're just talking. If you wanted to go 10 trillion units, okay, well that's describing a circle of x length. That's all. A circle of x size. So you're describing the ratio of a particular size circle's diameter to its circumference. Problem solved.
I think that makes a lot of sense. Now, but yeah, so I'm just what I'm thinking is something like, yes, you can say something like you don't need it at all. What I'm immediately what I immediately think of though is that the literally like the number pi shows up in so many equations.
Yeah, yeah.
So you have to think about these things in a different way because then
Well,
it's like,
yeah.
well, that's not a number, and that means the equation you're drawing here isn't what you think it is. So what
Well,
is it then? That
yeah.
has to be
Put
all of
put
that sort of stuff has
put
to
it.
be sort of redone.
I think what it's doing is it's capturing a general concept of circularity or sphericity that can be understood in a discrete context. So
Yeah,
so when I say you don't need pi, you don't need the transcendental pi, but the concept of circularity, I mean, obviously comes up everywhere.
yeah,
So you still have circuit. So the discrete pi captures circularity, but it captures actual circularity,
yeah.
not magical circularity.
Yeah. Yeah, that makes a lot of sense. Yeah, that's exactly right. Yeah. Yeah. That's interesting.
Okay, I feel like this is an awesome note to end the conversation on. This has been thrilling. I am so glad we ended up here. It's wonderful to be able to talk about this with somebody, because I've literally traveled around, Ryan, and talked to mathematicians on different continents about related subjects, and nobody, with a couple of exceptions, Weilberger's one of them. Nobody quite sees this diamond in the rough, and you're already there. You've already seen
Yeah,
it. You've thought
totally, man.
about
I,
it,
I
so
love
it's so
talking about
exciting.
this with you. Yeah, it's like I have literally never been able to relate to anyone about this subject other than you. I mean, I don't know why more people appreciate this. I can see why you think like every time you talk with like either a mathematician or a computer engineer, I can see there's so many people that just don't look they're not really trying to understand what's going on because if they did, more people would be aware of this and would talk
I
about this
think
all the
so.
time, I feel.
Oh, oh, it just popped in my head. It wasn't okay. The train ran off the tracks, but it turns out it was a separate track. It had only looked like it was disaster, and it's back on the track now.
Okay.
Because what you just said,
Yeah.
that reminded me of a funny story we should end on. Okay, because you
Yeah.
were talking about mathematicians and physicists sweeping things under the rug. Okay, I had a conversation with a gentleman we had a recorded conversation, we had a not recorded conversation. And he told me, won't say who he is, but he told me, with a completely straight face, nice guy. He said, Steve, he got his PhD in mathematics from a top university in the world. And he said, when I was there, people knew that mathematics was kind of a game. And because we were talking about these concepts, and he had similar intuitions, like, yeah, there's problems with infinite sets. And he said, but when he was having conversations at this top university, he said they were self-aware that this is a game being played. So
So they're just assholes. In other
or
words.
they're not clear
Yeah.
thinkers. The clear thinkers
Okay.
are like, okay, well, we have to appease whatever thing we're appeasing, But we know, yeah, there's some fundamental problems here that we are consciously aware of. Isn't that fascinating?
Yeah. It's fascinating. It's a little disappointing to hear if they really see it that way, like, oh, they're just playing some academic game. Like that's what I'm hearing from you, like as though they're not don't even really care about the math at all, that they're just playing some sort of status game or something, and they're even aware that that's what they're doing. It's
That's what he
terrible.
told me in hushed tones and was like, that's why I can't say who it was. It
That
was like,
explains a lot.
right?
This is the problem with academia. It's like 99% status seeking. They pretend to be the honest, truth seeking people. There's nothing about it's they're no more honest or truth seeking than anybody else.
Agreed, agreed. Well, again, this has been delightful. I won't take any more of your time, but
Well,
thanks.
thank you
What
so
a
much
blast.
for the conversation. Yeah, well, absolutely wonderful. Yeah, we'll hopefully we'll touch base again at some point. Let me know when you put it up, and I'll link to it. And yeah, hopefully we can touch base again at some point because it'd be cool to gradually build on these ideas, and maybe make something come of all this.
Definite.